The Webb companions are so far out that the light reaching us has been traveling for in excess of 13 billion years. Anyway, the universe has been extending, and in this way, the light has been stretching as well. For the most far-off universes, we are thinking back in time almost to the Big Bang. The vastness of the universe may appear to be tremendous, but every single piece of it started from what we refer to as the singularity. At this point, this is how we interpret the Big Bang hypothesis. The James Webb Space Telescope, JWST, has uncovered huge mysteries about the birth and evolution of the universe, leaving us awestruck. Popular physicist Brian Cox has announced that the striking discoveries made by the JWST could reshape our perception of the universe as a whole. Join us as we dive into these new heavenly revelations that promise to disrupt our understanding. The James Webb Space Telescope, named after the distinguished NASA Administrator James E. Webb, stands as a marvel of modern astronomical research. This telescope represents a huge technological leap forward from its predecessor, the Hubble Space Telescope. Resulting from a collaborative effort between NASA, the European Space Agency, and the Canadian Space Agency, the JWST surpasses the abilities of its predecessor. It uses cutting-edge technology and a design optimized for examining the universe in exceptional detail. Unlike the Hubble, the JWST delivers clear and sharp images of distant celestial bodies, working primarily in the infrared range. This unique feature allows it to penetrate cosmic dust and capture stellar objects that were previously hidden from our view. With its massive 6.5-meter primary mirror made from 18 hexagonal segments, the JWST dwarfs the Hubble's mirror in size. Positioned roughly 1.5 million kilometers away from Earth at the second Lagrange point, L2, it orbits the Sun in a state of equilibrium with Earth, ensuring a stable and consistent view of the universe. While exploring the farthest corners of the universe, the JWST also enables a kind of time travel. It uses infrared instruments to observe celestial objects and events dating back billions of years. The light emitted by these objects, stretched due to the expanding universe, undergoes a redshift, shifting from the visible spectrum to the infrared range. Fortunately, the JWST can detect this infrared light emitted by celestial bodies at extreme distances, allowing scientists to study the birth of stars, examine galaxy formation, and explore exoplanet atmospheres. Its latest remarkable discovery includes identifying an enormous cluster of galaxies at the edge of the observable universe. This finding challenges the validity of the Big Bang theory, prompting a reassessment of our core cosmological assumptions. To better understand how we arrived at this point, let's take a brief journey through the history of space exploration. Early civilizations, like the Greeks and Chinese, laid the foundation for understanding planetary motion by observing celestial bodies. Newton's laws in the 17th century provided a theoretical framework for space travel. In the mid-20th century, Edwin Hubble, an influential astronomer, made groundbreaking discoveries in cosmology and observational astronomy. His observations revealed that distant nebulae were separate galaxies far beyond the Milky Way, transforming our understanding of the universe's size and expansion. Hubble's law, formulated by him, showed that galaxies farther away were moving away at higher speeds, providing evidence for the expansion of the universe. The post-World War II era marked the beginning of the space race, with the Soviet Union launching Sputnik in 1957 as the first artificial satellite in orbit, Yuri Gagarin's orbital flight in 1961, and the Apollo 11 moon landing in 1969 as milestone achievements. Fast forward to 1990, the Hubble Space Telescope was launched, providing unprecedented clarity and stunning insights into the universe. The journey from ancient observations to the technological wonders of the James Webb Space Telescope highlights the steady improvement in our understanding of the universe. It has revealed the vastness of space and transformed key ideas in astronomy. Take the Hubble Space Telescope, HST, for example. It captured the famous Pillars of Creation image in the Eagle Nebula, revealing a stellar nursery formed by massive columns of gas and dust. Another key achievement was the Hubble Deep Field, capturing thousands of galaxies in what appeared to be an empty patch of space. The HST also probed exoplanet atmospheres, identifying elements like water and organic molecules in distant worlds, hinting at the possibility of habitable zones beyond our solar system. Following the discovery of the nearest observed supernova, SN 1987A, it shed light on the life cycle of massive stars. These accomplishments cemented the Hubble Space Telescope's legacy as a cornerstone of modern astronomy, captivating the world with its astonishing cosmic discoveries. Its successor, the James Webb Space Telescope, JWST, was launched to build on technological advances and lessons learned from Hubble. One example is our understanding of the universe's origins, which is today explained by the prevailing Big Bang theory. Around 13.8 billion years ago, the universe began as a hot and dense singularity, rapidly expanding and resulting in matter, energy, and fundamental forces. As the universe expanded, it cooled, leading to the formation of particles, stars, galaxies, and the various structures observed today. Despite being widely accepted, the Big Bang theory faced skepticism and challenges in its early years. Alternative models, such as the steady-state theory, propose a universe without a specific beginning. Concerns arose about evidence supporting the initial singularity, the expansion mechanism, and observed inconsistencies. Many of these issues were addressed over time, with critical evidence coming with the detection of cosmic microwave background radiation in 1965, aligning with Big Bang predictions. Space missions like COBE and WMAP, alongside technological advances, further supported the theory. The James Webb Space Telescope, equipped with advanced infrared instruments, can look through cosmic dust clouds, working primarily in the infrared spectrum. The JWST captures the oldest light in the universe, observing objects formed shortly after the Big Bang. Its infrared capabilities allow it to focus on star-forming regions, stellar nurseries, and the birth of stars previously obscured from optical telescopes. Infrared light, with longer wavelengths than visible light, penetrates interstellar dust clouds, overcoming a limitation of the Hubble Space Telescope. The JWST can detect cooler objects emitting primarily in infrared, making it ideal for studying phenomena such as exoplanets, brown dwarfs, and distant galaxies. As celestial bodies move away, their emitted light stretches, causing a redshift. The JWST's infrared capabilities detect these redshifted signals, capturing light from the early universe and providing insights into its formation and evolution. Exciting events, such as black hole formations or the birth of new stars, predominantly emit in the infrared range, further expanding the JWST's observational potential. The telescope complements optical telescopes like Hubble by offering enhanced sensitivity and the ability to detect infrared radiation. This capability allows it to peer deeper into space and delve further into cosmic history, revealing hidden celestial wonders and offering a broader perspective on the universe's development. The JWST serves as our window into the earlier stages of cosmic evolution. Recently, it revealed something so astonishing that it could prompt a re-evaluation of the entire cosmological model of the universe. Massive clusters of galaxies have been discovered at the very edge of the observable universe. These ancient galaxies existed only a few 100 million years after the Big Bang, situated at what is known as the cosmic dawn. The most surprising aspect is that we are unsure how such massive structures could have formed so early in the universe's history. This discovery might lead us to rethink our understanding of galaxy formation and evolution in the early universe. Studying early galaxies is crucial for unraveling the mysteries of cosmic origins. The JWST provides insights into how galaxies, stars, and planetary systems emerged and evolved over billions of years. These observations also contribute to broader questions about the fundamental nature of the universe, including its composition, structure, and the forces governing its expansion. While the Hubble Space Telescope was revolutionary for its time, it had limitations in observing the early universe. Its primary constraint was its inability to penetrate cosmic dust effectively and detect the infrared light emitted by ancient galaxies. Older telescopes relied on visible and ultraviolet light observations, which made it challenging to explore the early universe where these wavelengths are absorbed or distorted by cosmic dust and gas. The James Webb Space Telescope represents a monumental leap forward in observing galaxies from the universe's earliest stages. Unlike its predecessors, the JWST can observe celestial objects that formed within a few 100 million years after the Big Bang. Using its infrared sensitivity and advanced imaging capabilities, the JWST has uncovered an abundance of ancient galaxies, offering unprecedented clarity and detail in understanding the universe's infancy. With its groundbreaking discoveries, the JWST is reshaping our understanding of cosmic history. From exploring the early stages of galaxy formation to examining the atmospheres of distant exoplanets, this marvel of technology continues to push the boundaries of what we know about the universe. As we continue to analyze the data provided by the James Webb Space Telescope, we are reminded of the vastness and complexity of the cosmos. Every discovery offers new opportunities to deepen our understanding of the universe, our origins, and our place within it. Mixed waves in laid-out cosmological models with itemized information are testing a few parts of winning speculations and inciting cosmologists to reconsider core principles governing our understanding of cosmic development and structure. Inconsistencies between observed data and theoretical predictions have ignited intense debates among mainstream scientists. JWST, James Webb Space Telescope. Observations have revealed a larger number of galaxies in the early universe than anticipated by existing models, suggesting a more complex and rapid development process. Some observed early galaxies appear surprisingly mature, challenging conventional models that predicted slower development. The discovery of a massive cluster of galaxies challenges the expected distribution and arrangement of large-scale structures, unveiling a more intricate and denser cosmic web than previously thought. These observations raise intriguing questions and open avenues for further investigation. The presence of massive structures challenges early models of large-scale structure formation, prompting experts to refine models for better explanations. Understanding how such colossal structures formed so quickly after the Big Bang presents a puzzle that requires explanations consistent with key principles of cosmology. Significant disparities in the early universe's state compared to predictions based on existing models have also been uncovered. These differences may suggest previously unknown physical processes, unexpected conditions, or unidentified galactic phenomena. Simply put, these variations have prompted scientists to rethink and improve our models of the universe. At present, all we can say is that further investigation is required to integrate these astonishing observations into a more comprehensive understanding of the universe's origin. Observations often provide exciting glimpses into the universe, but in-depth analysis sometimes reveals discrepancies. For example, initial observations could indicate specific properties or features within distant galaxies that, upon closer examination, reveal differences in their formation, structure, or evolutionary pathways. In basic terms, cosmic phenomena are incredibly complex and require careful study to truly understand their nature. Spectroscopy, a technique that unravels the properties and history of celestial objects, is one example. It involves analyzing the light emitted or absorbed by celestial entities. By examining the properties of this light, spectroscopy provides detailed information about the chemical composition, temperature, density, and motion of celestial bodies. This analysis helps us understand the origins, evolution, and contributions of these objects to the cosmic tapestry. The JWST has uncovered various instances where initial observations differed from later analyses. For example, early observations of distant galaxies suggested a basic composition dominated by light elements like hydrogen and helium, consistent with theoretical expectations. However, spectroscopic analysis using the JWST revealed fascinating variations in elemental signatures, identifying heavier elements or compounds previously undetected or underestimated in the early universe. This challenges conventional ideas about the early universe's chemical makeup and the processes responsible for their formation and distribution across cosmic distances. Initial assumptions about galaxies in the early universe were based on basic observations, suggesting a relatively uniform pattern of evolution and organization. However, broader studies by the JWST uncovered a far more diverse and complex range of structural designs within these galaxies. These differences have reshaped our understanding of evolutionary pathways, suggesting that the forces governing the structure and evolution of galaxies in the early universe may be far more intricate than previously thought. On the other hand, the JWST has also confirmed several earlier theories and observations. For instance, spectroscopic measurements by the JWST confirmed the presence of hydrogen, helium, carbon, oxygen, and nitrogen within celestial objects, supporting theoretical predictions. These findings align with the widely accepted lambda-cold dark matter (lambda CDM) model, which suggests the universe began with a Big Bang and consists of standard matter, and dark energy. However, some predictions of this model have been tested by recent JWST discoveries. Alternative possibilities, like the cold dark matter model, which posits that most of the universe's matter is dark matter, are being considered. This elusive matter, unlike ordinary particles, does not interact with electromagnetic forces but exerts a gravitational influence. The model aligns with our understanding of cosmic microwave background radiation on a large scale, but encounters challenges at smaller scales, where discrepancies exist regarding galaxy structures and the abundance of small satellite galaxies around larger ones. Another proposition is the quasi-steady-state cosmology, which suggests the universe follows a repeating pattern of continuous expansion and contraction, challenging the Big Bang singularity. This model remains speculative due to its deviation from traditional models and the lack of direct observational evidence supporting its cyclical nature. The mirror universe hypothesis proposes the existence of an identical parallel universe alongside our observable universe. This model suggests the mirror universe may have its own distinct physical laws and particles, offering an alternative explanation for various cosmic mysteries. However, it lacks observational evidence or test data and remains largely speculative. The digital simulation theory proposes our universe could be a complex computational simulation. Advocates argue that our reality may be a highly advanced simulation, akin to virtual reality. This idea stems from philosophical considerations and faces challenges in providing observational confirmation or disproof. Finally, the multiverse hypothesis proposes the existence of multiple universes, each with its own unique set of physical laws and properties. Our universe is just one among an infinite number of universes, each with different constants and possibly dimensions. While intriguing, we cannot directly observe or access other universes, making it speculative. While alternative cosmological theories may not be as widely accepted as the lambda CDM model, it's essential to remember that even the latter faced skepticism early on. Confirming or refuting these speculative theories is challenging, but they may warrant consideration if our current cosmological model falters over time. Recent discoveries, though enlightening, have not disproven the Big Bang theory. According to many experts, observations from the JWST have enhanced our understanding of cosmic history, aligning with Big Bang predictions. Massive galaxy clusters at the farthest reaches of the observable universe suggest gravitational forces were operating even in the early universe, consistent with Big Bang expectations. The presence of these massive structures at the edge of the observable universe implies their light has traveled billions of years to reach us, offering a glimpse into the universe's past and supporting the theory's predictions about its evolution. However, these observations also present inconsistencies that merit objective scientific investigation. The JWST has opened new vistas, allowing us to explore the ancient realms of the universe. These groundbreaking discoveries by the JWST not only challenge established cosmological principles, but also emphasize the dynamic nature of scientific inquiry. The unexpected findings regarding early galaxies, their rapid formation, and their chemical diversity necessitate re-evaluating the models that describe the universe's evolution from its inception. While existing theories like the lambda-cold dark matter, lambda CDM, model have provided a robust framework, The anomalies discovered compel researchers to refine these frameworks or even consider alternative models. The role of advanced observatories and technologies. The JWST has highlighted the transformative potential of advanced observatories in unraveling cosmic mysteries. Its ability to capture faint infrared light from the earliest epochs of the universe enables researchers to probe regions and time periods previously inaccessible. Combined with sophisticated techniques like spectroscopy, astronomers are now equipped to map the physical, chemical, and structural evolution of celestial bodies with unprecedented detail. Future telescopes, such as the European Extremely Large Telescope, ELT, and the Nancy Grace Roman Space Telescope, promise to complement JWST's capabilities by observing the universe at different wavelengths and scales. Together, they aim to create a more holistic view of the cosmos, potentially resolving current discrepancies and uncovering even more profound insights. Theoretical revisions and new horizons. 1. Revised models of galaxy formation. The unexpected maturity of galaxies in the early universe suggests the need for modifications to current galaxy formation theories. Faster cooling mechanisms, more efficient star formation processes, or interactions involving dark matter and exotic particles could explain these rapid developments. 2. Chemical complexity in the early universe. Observing heavier elements in early galaxies challenges long-held assumptions about nucleosynthesis following the Big Bang. This could indicate alternative pathways for element formation, possibly involving population 3 stars. Hypothetical, massive, and short-lived stars thought to have existed in the universe's earliest phases. 3. Rethinking the cosmic web. The denser and more intricate cosmic web structure observed suggests that gravitational interactions, dark matter dynamics, or unknown forces might play a larger role in shaping the universe than previously assumed. 4. Multiverse exploration. Although speculative, the multiverse hypothesis gains attention as an intriguing framework for addressing anomalies that cannot be explained within a single universe model. If multiple universes exist, they could offer alternative explanations for variations in physical constants and the distribution of matter. 5. Emerging quantum cosmic connections. The intersection of quantum mechanics and cosmology continues to be a fertile ground for exploration. Some theories propose that quantum fluctuations in the early universe could have left imprints visible today, influencing the distribution of galaxies and cosmic microwave background radiation. Philosophical and existential implications. The discoveries also provoke deeper philosophical questions about humanity's place in the universe. If the multiverse exists, are we merely inhabitants of one of countless realities? If the digital simulation hypothesis holds weight, what are the ethical and metaphysical implications of living in a constructed reality? These questions push the boundaries of science, philosophy, and theology, encouraging interdisciplinary dialogue. The future of cosmology. As we continue exploring the cosmos, collaboration across disciplines will be essential. Astronomers, physicists, chemists, and data scientists must work together to integrate observational data with theoretical models. Furthermore, advancements in artificial intelligence and machine learning are poised to revolutionize data analysis, enabling researchers to identify patterns and correlations in vast datasets that would otherwise remain hidden. Human curiosity and ingenuity remain at the heart of cosmological discovery. The JWST, along with future missions and theoretical breakthroughs, underscores the limitless potential of human exploration. While many questions remain unanswered, the pursuit of understanding the universe continues to inspire and unite humanity in its quest for knowledge.